Hey, welcome back. Haven't filmed a video in a couple of weeks at least, but couldn't find anything on YouTube that was really trying to explain what I'm trying to do here. So I'm going to do this one myself. So anyway, this next section is on continuity, and this is more so like doing proofs, a little different than what you did in grade 11 with triangles. But still, we're doing some proofs, proving that something, a function is continuous or not continuous. And that's what we're going to do in this next section. So first of all, I want to just kind of remind you about continuity versus discontinuity. And what we have in front of us right here is a graph, a piecewise function that has different pieces. And you can see here that this graph is discontinuous in a number of different places. So what I've done here is I've listed the 4 different x values at which this graph is discontinuous. It is continuous everywhere else. But once again, okay, if you have to lift your pencil off of the page in order to continue drawing the graph, then you can consider it discontinuous. So you can see that happen at 4 different x values here. I've given names to each of these types of discontinuity. I don't think these names ever come up in any questions or anything like that, okay? But just so you know, there are different ways of being discontinuous. So starting on the very left here, as I travel throughout this graph, I run into my first discontinuity at x is equal to -2. And you can see that there is a POD right there at -2. You can call that a POD. But because the point is elsewhere, the actual point is down at -2, -2. So you can see right here as I make this point a little bit larger, it's like the point was removed from where the POD is now and placed somewhere else. And that's why they call that a removable discontinuity. And then at -1, there's a jump where it stops and then drops down to the negative area. Okay, so at -1, there's a jump discontinuity. And then at +2 for x, you see a vertical asymptote. That's also known as an infinite discontinuity because the graph is approaching infinity on the left side, and then on the right side, it's approaching -infinity. So we can call that an infinite discontinuity, or you can say there's a vertical asymptote, or you can say nothing, okay? I don't think these terms are really going to come up in any questions. And then same thing at x is equal to 4. There's also discontinuity there. That is a POD. And I didn't call that a removable discontinuity because you do not see that point that is missing. You don't see that elsewhere on the graph. Okay, so you just see, really what you want to get from that is you can just see visually where a graph can be discontinuous. And next up, okay, we have a formal definition of continuity. And a function is continuous if it meets all 3 parts of this definition. So if one of these parts a function does not meet, then it is discontinuous. So you have to have all 3 checked off in order for a function to be continuous at a given point. So the point has to exist. The limit as x approaches that x value also has to exist, meaning the right and left hand limits are equal. And as well, okay, the values that you get for the first 2 points have to be equal. So the point and the limit have to be equal to one another. And if it satisfies all 3 conditions, all 3 criteria, then it is a continuous function. If it fails the first point, you do not have to go any further. Once it fails one of these points, then we can say the function is discontinuous. So sometimes you'll get an answer right away at the first point. Okay, if f of c does not exist, then you can stop right there and say it's discontinuous. Sometimes you have to go all the way to the 3rd point before you can say a function is discontinuous. So you're going to see that in the next video. We're actually going to go through several proofs together in the next video using this definition.